These notes are going to go over how you determine whether or not a covalently bonded molecule is polar or nonpolar. So the first thing to remember is that electronegativity values help us determine whether or not a bond, a single bond, is polar or nonpolar. So we'll look at just two examples to sort of refresh. If we're looking at carbon and sulfur over here, if you were to look up their values on a electronegativity table, you would see that they both have an electronegativity of 2.5. That means that this bond between them is nonpolar, meaning that electrons are being shared equally between the two of them. Versus hydrogen and fluorine over here. Hydrogen has an electronegativity value of 2.1. Fluorine has an electronegativity value of 4.0. Fluorine being much more electronegative than hydrogen, when they share electrons, shares them unequally. So the electrons are closer to the fluorine. That's going to give fluorine that partial negative charge, and that leaves hydrogen with the electrons further away from it with a slight positive charge, forming a dipole, meaning two poles, a slightly negatively charged pole and a slightly positively charged pole. We can also show this dipole by drawing this arrow in the top, always pointing at the more electronegative atom, with the plus or cross here in the back toward the less electronegative atom. So in this case, this would be a polar bond because fluorine is sharing the electrons unequally with hydrogen. Now, that is not the only thing that we need to consider when we're looking at a full molecule, because some molecules have more than one bond. So we'll also have to use our knowledge of Vespers. So we'll use our knowledge of polar and nonpolar bonds along with our knowledge of Vesper shapes. So we learned 5 of them: linear, bent, trigonal planar, trigonal pyramidal, and bent. And we're going to use our knowledge of those shapes to also help us determine whether or not the molecule will be polar or nonpolar. Now, polarity is going to end up being important because it tells us how molecules are going to interact with neighboring molecules, and we're going to be talking about that further on in this week. So the first thing, I always like to break it down into 2 main steps. So the first step is to determine whether or not the bonds in your molecule are polar or nonpolar. So if my bonds in my molecule are nonpolar covalent bonds, so if every bond in my molecule is a nonpolar covalent bond, then the molecule will be nonpolar. So if they're all nonpolar bonds, so here's an example: carbon is 2.5 electronegativity value. Each sulfur has a 2.5 electronegativity value. That means between this carbon and this sulfur, they're sharing all of their electrons equally. And between this carbon and this sulfur, they're sharing all of their electrons equally. So all the electrons are being shared very equally amongst everybody, and so no poles are being created. So this whole molecule will be nonpolar. So if all the bonds are nonpolar, then the whole molecule will also be nonpolar. So again, I wrote that down here: all nonpolar bonds. Therefore, those 3 dots together is the symbol for therefore. Therefore, it is a nonpolar molecule. Now, what happens when polar bonds are present? When polar covalent bonds are present, then we have to start looking at the shape. So if the molecule is symmetrical, what will end up happening is the dipoles will cancel and the molecule will end up being nonpolar. So even though polar covalent bonds exist, if they cancel, then it will be nonpolar. So I've got 2 examples here. I've got CO2. So carbon has an electronegativity value of 2.5. Oxygen has an electronegativity value of 3.5, and I've got one here on the left side and I've got one here on the right side. So I'm going to look at this bond first on the left side, and I see that oxygen is the more electronegative one. So it creates a dipole going to the left. Now, if I look at the other side of the carbon, it is also bonded to an oxygen, and it is creating a dipole going to the right. Now, if this oxygen is sharing unequally a little bit close to it, and if this oxygen is sharing an electron a little bit close to it, the electrons aren't generally shifting in just one direction. Some of the electrons are shifting to the left, and some of the electrons are shifting to the right. So what ends up happening is they cancel. So the pull to the left and the pull to the right end up canceling out. And because those dipoles cancel, this is considered a nonpolar molecule. All right, so let's do it again. So trigonal planar. When I'm looking at BF3, all of the fluorines are pulling in opposite directions of one another. You can imagine like if you were playing tug of war and this was your pit and somebody were pulling on your rope in this direction, in this direction, and in this direction, all with the equal amount of strength, that means that nobody would really move. And that's the same for the electrons. So even though fluorine has a much, much higher electronegativity than boron, this fluorine is pulling the electrons in this direction. Again, sort of like a tug of war. This fluorine is pulling in this direction, so slightly down and to the left. This fluorine is also pulling down and slightly to the right. And so because all of these fluorines, all these are pulling with the same amount of strength, the electrons that are being shared around boron, they're not actually moving in any particular direction because, again, it's like a tug of war. So if we're being pulled this way, and this way, then the electrons really aren't going to move in one particular direction. So since all of these dipoles, which are moving in opposite directions, cancel, the molecule is considered nonpolar. So even though there are polar covalent bonds that exist, if they are moving in opposite directions, then they are canceling. Now, opposite directions can be going left and going right. They can be going up. They can be going down. They can even be pointed in toward each other. This arrow is pointed to the right. This dipole is pointed to the left. This is still opposite directions. That means that they are still canceling. So if all of your arrows are pointed in opposite directions, the dipoles are going to cancel and your molecule will be nonpolar. Now, if a molecule with polar covalent bonds, so we're still talking about molecules that have polar covalent bonds, if a molecule with polar covalent bonds is not symmetrical, the dipoles will not cancel and that molecule will be considered polar. So I've got two examples up here, and then I've got some shapes that I wanted to talk about down here. So in this case, I still have something linear, right? But this carbon in the middle has an electronegativity of 2.5. Hydrogen has an electronegativity value of 2.1. And nitrogen has an electronegativity value of 3.1. So I'm going to look at carbon and nitrogen, and I see that nitrogen is a more electronegative one. So it creates a dipole moving toward nitrogen. Now when I look at carbon and hydrogen, again, I see that there's a difference in electronegativity. And carbon is more electronegative, and so technically is making a dipole going again to the right. Well, if both of these are going to the right, there's nothing canceling it out, so this ends up being polar. And again, the direction that the arrows are pointing in is the direction that gets the partial negative charge, and the other side of your molecule, which would be this side over here, ends up with the partial positive. So because the dipoles do not cancel, this ends up being a polar molecule. I've got one more example over here. This is sort of a complicated one, but I wanted to show you one anyway. So in this particular example, my molecule is actually somewhat symmetrical, but let's check out our dipoles for a second. So what ends up happening is that carbon here has an electronegativity of 2.5. And chlorine has an electronegativity of 3.1. So chlorine is pulling on those electrons harder than carbon. So it's creating a dipole in this direction. Now, the only way to cancel this out is to have dipoles going in the opposite direction, meaning pointed down. So I'm going to look at carbon's bond with hydrogen. Hydrogen has a electronegativity of 2.1. We would actually consider this nonpolar, but just for the sake of this particular example, Let's just say that they're being shared unequally, and that dipole is moving up toward carbon. So it's slightly up and to the right. This hydrogen is also less electronegative than this carbon, so it's going to be pulled up toward carbon. And this hydrogen is also less electronegative, so the electrons again are being pulled up toward carbon. And you'll notice that all of the dipoles are moving in a slight upward direction. That's going to give this region up here a partial negative charge, and this region down here by your hydrogens, the partial positive. Even if you consider these particular dipoles nonpolar, we can see that there is still no dipole canceling out this upward vector. There's no downward dipole. So this would still be considered a polar molecule because of this polar bond that is happening here that is not getting canceled out. Now there are some particular shapes that are more likely to be polar. There are two of them, in fact, that we've learned about. Trigonal pyramidal and bent are oftentimes, if there are polar covalent bonds, these will often be polar molecules because it's hard to have anything cancel them out. So again, even though this is actually somewhat symmetrical looking, trigonal pyramidal will often be polar, and that's because of that pyramid shape that it makes. So in this case, nitrogen has a 3.0 electronegativity value, and each hydrogen is 2.1. So these are all polar covalent bonds. And in this case, they're all going to be moving toward nitrogen because it has the higher electronegativity. They're all going to be upward arrows, and because they are all going upward, you would need a downward arrow to cancel it out, but there can't be a downward arrow because of the shape here. There's only these electrons hanging out up here. So all the dipoles are moving in this slight upward direction. That's going to give your nitrogen that slight negative partial charge up here. And that means down here by your hydrogens, you're going to have that partial positive charge. Bent is very similar because of that fact that it has that shape where your vectors are either going to be moving up or they're going to be moving down. In this particular case, they're going to end up moving up just because of the example that I've made. So here we have H2O. Remember, it is a bent shape, so these are at a slight angle. And it's really important that you draw your Vespers here because the Lewis dot diagram looks different than the Vesper drawing. And because of that, you can only use your Vesper drawings to determine polarity. So oxygen has a electronegativity value of 3.5. Hydrogens are at 2.1, so oxygen is more electronegative than hydrogen. So you get that dipole moving up toward oxygen. That means that this region up here toward oxygen will have that slight negative charge because there's no downward arrow canceling it out. And that also means that down here by your hydrogens, you'll have that slight positive charge. So this pole will end up being slightly positive compared to this pole. So up here, slightly negative, down here, slightly positive. Now, just so that we're really clear, if you had these are just made up elements, if you had a bent shape or a trigonal pyramidal, there's a chance that if your electronegativities are greater down here than up here, your dipoles would be moving in the downward direction. This would still result in a polar molecule. It would just be slightly negative down here with a slight positive charge up here. So it doesn't have to be the slight negative charge at the top. It could be down here. It all depends on those electronegativity values of your different atoms.